C'est normal comme vous voyez. C'est lui?
Si tu as encore un port USB, il y a le pointeur. Si tu veux.
Ah, merci beaucoup. Mais du coup, on voit pas. Ah, c'est trop bien. So my presentation will be in English for the people. So thank you for having me today. My name is FERRADJ Imane, and I'm supervised by Nazih Mishbal, Eric Montero, and Sébastien Roland. And I will present you a work around how to reconstruct for the polarization loop of a ferroelectric actuator via curvature without the need of measurements of the currents. And this work is conducted through my PhD work. I'm currently a third year. So let us start with the context. So the motivation of this work revolves around the application of PVDF, TRFE, CTFE relaxer terpolymers, which are very interesting materials for developing soft continuum robotics dedicated for mini surgery applications such as telecystoscopy. And so the particularity of these materials is that they are huge electrostrictive materials and they are good in actuation. And in robotics, we really care about fast actuation within a few seconds and also important range of actuation. So in this work, we focus more on the actuator and not on the robotic system. And this is why we use a unimorph structure that is, I'm not able to see, it's huge. Like the structure, the beam. So I would have a passive layer, which represents the substrate. On top of it, I will have the active material, which is the relaxer terpolymer. And the idea is that in order to control the motion of the actuator, we need to know actually what the polarization electric field loop looks like, because it's one among the nonlinearities characterizing the used material. And so the idea is instead of measuring for the currents and deducing for the polarization hysteresis, we actually exploit the curvature data in order to extract this information. Because for one actuator is okay, we can add an amplifier to measure for the currents. If I have a whole structure, or would have 6 actuator structure, it becomes very cumbersome to deal with multiple devices. And so, as you can see, this is a classical way of measuring characterizing for the measured currents to extract actually for the polarization loop. In the total measured currents, we have 3 components. We have the ferroelectric current, which what we want to extract. And we have the 2 other currents, which is the capacitive current and resistive leakage currents. And in this material specifically, they actually become very hard to isolate, to remove, because the whole current becomes noise sensitive. And so the leakage capacitive term becomes very hard to fully remove from this quantity. And this is actually the curve we want to exploit. So in blue, we have the curvature versus the voltage. And this is the data we want to use to extract for the curvature. And at the same time, using an analytical model to actually write this curvature into sums depending on the physical effects present in the actuation. We have electrostriction, and we have another phenomena called the Maxwell effect that I will introduce later. So an overview of the workflow of the method developed here. So the first thing is to measure for the center line during actuation through image processing, or depending on the sensor you want to use to measure for the curvature. So it's estimating the curvature, and then identify some parameters that are part of the model, which are the electrostrictive coefficients and the permittivity, the relative permittivity, which is another model constant, and some, I will call this a small gap to guarantee that the loop is symmetric. After that, we remove the Maxwell effect, because what relates the curvature to polarization is electrostriction that is quadratical to the hysteresis, the polarization. And the next step is recover the sign, distinguishing the ascending and descending branches of the loop. And finally, the inversion via a simple parabolic formula. So few general information. We need zero current sensors. We only track for curvature. The numerical error on the polarization, the saturated polarization, is very small, around 0.1%. And experimentally, using a provided hysteresis loop measured with a TF analyzer, we have -6% of error. So the used model is very simple. It's a combination of electrical phenomena and mechanical parts. So the strain is the sum of electrostrictive quantity, which actually contains the information we want to reconstruct. And we have the Maxwell effect, which is due to the presence of the two electrodes sandwiching the active material. And so we have electrostatic force resulting into this term called Maxwell effect. Usually is neglected in some materials. In this case, we don't neglect for this material because we have high dielectricity and slightly low Young modulus. And this is the classical mechanical term. So combined with the classical laminate theory, since we have, how do we call this? A composite material. We can write the curvature as a term that directly links to the polarization, where C is defined by a term that is related to the geometry of the actuator called alpha beam. We call it alpha beam, multiplied by the electrostrictive coefficient, and the second term, which represents the Maxwell effect, which, if not accounts, then the obtained hysteresis loop is contaminated or overestimated. And beta here is simply the alpha beam, once again, doubled by other physical material parameters. So the idea is to make sure we remove this term called Maxwell contribution, because electrostriction and Maxwell usually looks kind of alike, but we need to make this distinction. So the algorithm starts with first correcting the measured curvature, and this is via removing this Maxwell effect. And so we would have something that is, let's say, curvature resulted through electrostriction. And then via the parabolic formula, we invert, we make an inversion to collect the hysteresis, the reconstructed hysteresis, and notice that we have a sigma parameter, which is either -1 or +1, and this actually is depending on whether if the branch of the hysteresis is ascending or descending. And so jointly, what we do is that we have parameters that are unknown, such as Q13 and εr, and a small gap that we define. And those are actually defined in parallel. The way they are defined is that we set a bunch of conditions or penalties to make sure that the collected parameters results in the correct reconstructed hysteresis loop. And so these penalties or conditions can be written into a general cost function that is minimized in order to obtain a unique decision vector. And so the first one is that the hysteresis at Vmax and like plus or minus Vmax should be closed, a closed loop. The second condition is that if we try to look at the loop curvature versus polarization to square, the regression should be linear and goes through the zero. And there shouldn't be overcorrection when the Maxwell effect removed, meaning that the corrected curvature should be always positive. Also, we need to guarantee the continuity near the switch-ins, near the coercive electric field. And we also add like reinforcements of these penalties. It is the soft symmetry for the hysteresis. We consider that the hysteresis is symmetrical. And this results into a final cost function that is minimized. And so the first layer of validation is numerical. So as you can see in the panel A, the regression between, so in points, it's what I actually draw. So the raw curvature versus the reconstructed hysteresis, we have a linear regression, which is a good sign. So we respected one penalty. And in B, actually, I verify the very simple analytic model versus a complete and more accurate model. Side note, the numerical validation is to like compare what has been reconstructed using the method I'm presenting versus a more accurate model, which is not really presented here because it has a lot of other details. But let's say this more accurate model is my ground truth, which I'm comparing to the reconstructed loop. And so I see that there is a good agreement between the complete model and the reconstructed, the very simple model of the curvature. And then because in my model, what I have to do first is to compute for polarization, hysteresis loop, to then obtain for the curvature, the resulting curvature once applying the voltage. And so here in panel C, I compare for the ground truth loop to the loop that has been reconstructed. And so once again, I see that I have pretty nice results, very promising result to go through the second layer of validation, which is experimental. And so the applied voltage was just a triangular sweep going to up to 500 volts and minus 500 volts. And the last panel shows that we should be very careful near the switching points because the error becomes considerably, a little bit high. So it shows that even though the result is promising, there will be some few issues near the switching points. And so the second layer is experimental. What we do is we track for the curvature through image processing, and at the same time, we don't look for we only look at the curvature at the tip of the actuator. So we use the pure relaxer here with an active thickness of 5 micrometers and 25 micrometers of substrates. And the thing to take into consideration about the experimental validation is that we do compare to experimental hysteresis loop that was measured via TF analyzer here in EMS and not in my laboratory PIM. We don't have this device. But it's not included in computation. It's only for the sake of comparison. And so here's the result. It has pretty interesting results. So the first thing in green is the ground truth data, the data that has been measured via the device. And in blue is actually what has been reconstructed through using the method. And I don't know if you can see, there is a slightly higher loop in gray, dotted line. And this is in case I didn't remove for a Maxwell effect. So I have a slightly bigger loop. And so I have few parameters that has been identified, which I don't consider them like a representation of the composition of the material that has been used, because apparently in electrorestriction we don't have a single parameter of a electrorestriction parameter. It varies because electrorestriction is slightly complex. So I have good agreements. And I'm happy now because I can use this as an estimator in a control strategy. And so regarding robustness, so what I can say is that near PSAT, or the saturation polarization, I have good results. And the curvature fits quality because right here. Yeah, because it directly tests for the mechanical model. However, there are some issues with the method, though it has some good results. It is that near the switching points, the switching region. Sorry, I illustrated using a ferroelectric loop because it's bulkier and easy to use to show the switching region, which is near EC. So EC and P are sometimes slightly not nicely defined. And yes, once again, Q13 and epsilon R shouldn't be interpreted as the real parameters of the chemical composition, but rather than just for the actuator that is used. And the core assumptions were that only the first mode of curvature was considered. And we assume that really electrorestriction follows this model, like proportional to the square of polarization. And that similarly, but Maxwell effect is captured with a relationship that is proportional to the square of electric field. So this method allows us to estimate for the hysteresis loop just through looking at the actuation from a macro scale level for us who work on robotic systems. And now it is easily for like a more complex structure to define for the hysteresis loop without needing for current measurements. And so the conclusion is that the method was first validated numerically and then experimentally by comparison to real data measured with the device dedicated for hysteresis measurements. And this can be applied as an estimator in control system. That's all. If you have questions, don't hesitate.
Unfortunately, we don't really have time for questions.
Oh,
I didn't want to stop you at the end, but
okay.
You can go and see Imane during the poster session. If you have questions for her, and we'll
Yeah.
close so we're not too late.